Howdy y'all, and welcome to a weird video. This weekend I'm doing a collab with Turbo Makes Games where we both produce a game for the Ludum Dare Game Jam. Him using Unity Dots and me using Bevy. I'll be live on his channel on Friday night, and I'll probably be up again after the jam, so check that out. However, this means I'm going to be writing Bevy for the full weekend, so I'm taking this week off to explore some other hobbies. Specifically, I went to college for computer engineering, and one thing I always loved was FPGAs. I also found the rust-hdl crate, which lets you generate and simulate FPGA designs using Rust, so I figured I'd check it out for the week. I wrote a simple VGA driver and text display system while trying out their crate, and I want to document and share what I did. I'm going to cover a ton of things here, from buying an FPGA, to different tools, to actually creating a design, so hopefully there's something here for everyone. This video is going to be more intro to FPGA and a little bit light on the Rust, but I hope you enjoy it anyway. I'm mostly just going to geek out about something I find really cool, so sit back and enjoy the show. This also turned into a long one, so please skip ahead with the chapters if you want to see the Rust or any of the cool designs. So first up, what are FPGAs? I'm assuming most of the viewers to this are my normal Bevy audience, so skip this section if you already know the basics. FPGA stands for Field Programmable Gate Array, which basically means it's reprogrammable hardware. Think of it like designing a CPU at the logic gate level. They have niche uses, but are often found prototyping future custom silicon designs in low-volume applications. The trade-off is that it's more expensive to buy an FPGA chip than a custom chip, but the creation of that custom chip has millions of dollars in design and startup cost. You'll often see FPGAs in military and medical designs where the total units are in the hundreds or thousands, but I've also found some in car GPSs, cameras, and the sensors that my wife uses for scientific work. Also check out the Mr. project, which uses a beefy FPGA to simulate mini game consoles and retro computers at the gate level. If you're interested in buying and playing with one, I would recommend the Basis 3 from Diligent. It's a bit expensive, but I think it's the happy medium for hobbyist FPGAs. The rust-hdl guys recommend the Alacrity CU board, but I'm not as big a fan of that one. First up, it's cheaper, but the connectors are less common, and you don't have any easy onboard toys to play with. Basis 3 has a 7-segment display, nice chunky switches, some buttons, a USB port for a keyboard, a VGA output, and a couple of general-purpose PMOD connectors. There's also the RDS7 board, which has a weaker FPGA but has some nice RAM and different connectors, and is a little bit cheaper. Another big difference to know when you're shopping is the vendors. Basically, you have Intel and Xilinx, now owned by AMD, which are your professional military-grade companies. These come with brutal tools and honestly hate open source. But then you have Lattice, which are cheaper and weaker FPGAs, but they support open source tools and are more organic, non-GMO style FPGA boards. Also, there's some system-on-a-chip style boards, which have full CPUs like ARM cores embedded into the silicon. These are super powerful, but in my opinion are a bit harder for beginners to get started with. There's also the option to use a soft-core CPU, which is basically giving up some of the programmable logic to use a pre-built CPU. Xilinx offers their microblade CPU, which is really interesting because you can actually customize the exact inputs, outputs, and other features you need, and then program it in C like any other CPU. Overall, in my opinion, the RDX7 is the dream FPGA chip for hobbyists. It's not too big and doesn't require an expensive license, but it's also not as weak as the Spartan versions, so you can do interesting projects. But you're not going to be running massive machine learning models on it. Also, these are professional tools, so get ready for the Xilinx forum answers to always point you to hundreds of pages of PDFs. There are dozens of user guides about everything from voltages to what different subcircuits of the FPGA do. These are all very interesting, but don't get overwhelmed by them. Eventually you'll learn which ones are useful or interesting, and which ones are just pages of voltage information you don't care about. Finally, tooling. I own Intel boards and Xilinx boards, and personally, I much prefer Xilinx tools. Lattice also has its own tooling and even supports open source tools that let you get all the way to flashing the board without having to use anything proprietary. But I don't really too much care about open source software for FPGAs. But if it's important to you, then check them out. But let's start actually looking at the Xilinx tooling now. Vivado is a beast, and is the Xilinx design suite for their modern FPGAs. To download it, you'll need to sell your soul to the US government because these are military grade toys, but I think it's worth it. I could talk for hours about Vivado, but basically you just follow the flow on the left of the screen to generate and flash your designs. Inside here, you can review and see exactly what's on the FPGA, and even exactly which parts of your design is used and how it's wired up. You can also simulate designs and see how signals are changing with time. Finally, you can even create block diagrams and use Xilinx pre-built design chunks, but I don't often play with this. There are tons of nuanced things to talk about here, like clocks. Basically, your FPGA has a heartbeat, usually around 100 MHz, and every time the heart beats, all of the memory cells in your design will tick over to the next value. But you must make sure that value is ready when the beat comes around, and Vivado will check the timings for you and report the worst timing slack. Vivado will generate tons of critical warnings all the time, but as long as nothing is read, it usually just works. This is honestly just a joy to play around with and explore, but it can be overwhelming at first, and today I'm actually not even going to use it at all. Instead, I'm going to use what's called a non-project workflow, where I don't even create a Vivado project. Instead, I'm just going to feed it a script to tell it how to eat the output of my rust-hdl program and flash it to the FPGA. I just grabbed this script from a blog and added the section to program the hardware by stealing the commands I saw Vivado running in its own console. Then I bundled this up into a script of cargo run, and as long as top.v contains a good design, then my FPGA will eventually be flashed with the design. We also need one more file which tells Vivado which signals in our design are going to connect to which pins on the actual chip. You'll usually get this from the person you bought the board from, and you just uncomment which pins you're using. Secretly, you can uncomment all of these and it still works, just Vivado will give you critical warnings about undriven nets, but who cares? I changed my signal names over to match what I'll use in Rust. Now I need a top.v file which will contain my design. The language I prefer to use for FPGAs is Verilog, which thankfully most hobbyists also prefer. The other choice is vhdl, which I've used for work before and is often used for military applications, but I think it's a miserable language. Not that Verilog is much better, but a single good cheat sheet is all you really need to write Verilog. These are hardware definition languages, which is what the HDL and rust-hdl stands for. These are basically ways of turning a drawn schematic into text. I really don't think you should view them as programming languages, and instead treat them as written descriptions of a circuit. So I'm going to come clean and say I honestly don't believe in things like rust-hdl. The idea is noble, Verilog sucks, and most of FPGA work is about simulation and so on. And there are always these attempts to wrap Verilog with a more common language, like MyGen does for Python, MIT made BlueSpec, and there's a Haskell one that I've used, and there's even a C++ one, which is horrifying. As I understand it, the main idea is to make it easier to simulate models, which is again a noble goal, but I don't think generating the Verilog from these is the right approach. When designing a circuit and hardware, it's a lot of worrying about which cycle everything is happening on. Remember the heartbeat from earlier? Yeah, so in a simple example, if I want to read from a RAM, then I'll set the read address, and now the data won't show up until one cycle later. Then let's say I do a multiplication and store the value. Now that value is also delayed by one cycle. You really need to think about this, and I think high-level synthesis just misses this core part of the design. Unless you've already done the work on paper, or in your head, I just don't really believe in it. But professionals disagree, and Xilinx is putting a lot of work into their own high-level synthesis flows, so maybe I'm just a boomer. Basically though, I'm going to use rust-hdl as a Verilog substitute in this video, and I've already done all my designs on paper. Now let's actually start looking at rust-hdl. My goal of this program is to generate simulation files and eventually the top.v file that I can turn into hardware and run on my board. First up, they have a great book with a quick start guide. I love it. Let's start with the simulation quick start. Here, we just need to create a strut, which will be our hardware module. We set up the inputs and the outputs, and we can even define internal flip-flops and wires. I guess I haven't talked at all about hardware designs, but I really can't teach my whole degree in one video. Ben Eater has a great series where he built a CPU from scratch, and I'd recommend checking out his videos if you need the absolute basics. For this video though, I'm hoping you can follow along even knowing nothing beyond what a circuit looks like. Basically, hardware design is a game of abstractions. You create sub-circuits called modules that have inputs and output wires and do a single task, and then you connect more and more of these together to make bigger designs. Blinky here takes in the system clock, which basically every module should do, and sends out one wire called LED. It also has an internal module called Pulsar, which is one of the many pre-built modules in rust-hdl. They provide modules that do common actions, which can be very useful if you don't know how to solve the fundamental problems yourself. Next, we need to define a default for our module. It seems this default function is where we do the setup for creating the module and its internals, but we don't do any wiring. Here, they just create a pulsar that will be on for 250 milliseconds out of every second. Then we implement logic for the module, and using the update function, design how it's going to be wired up internally. This actually gets turned into the raw Verilog circuit description, so there's tons of rules here. Currently, the error system isn't great if you break the rules, but basically you can't do things like create new variables, and it will ensure that every output is wired up to. This is where I think they're hoping to get value from Rust Type Checker, because it aggressively makes sure that bundles of wires are connected to the correct size bundles and enforces some other rules. But it's also missing some rules, like it could wire an input into itself, but overall it's an interesting experiment. Here, I strongly recommend having your design on paper and just implement it in code. You probably just can't write a hardware design from memory in the same way that you can normal code, and it's easier to draw the wires out on paper first. All they do here is wire the input clock to the pulsar clock using the next in val pattern. Then they wire the pulsar to always be enabled, and finally wire the LED output to the pulsar's output. Then they call a simulation macro, which we can explore in a future video, but basically I just want this output VCD file. These VCD files can be viewed in the viewer of your choice, but they can get rather big if you simulate for a long time. I can't go into all of the details here, but you can see the waveforms of various signals in your designs, and you can verify that everything is working exactly how you'd expect before you flash it to your hardware. Finally, in their book they have a chapter on generating Verilog, which is what I'm after. I change the signals in the block to match my board constraint files, and then write the top.v. Now, I run my Vivado script, and it becomes real hardware and my LED blinks. The output from Vivado is horrifically overwhelming, but is actually really cool. Specifically, you can see the utilization of the different subparts of the FPGA. You aren't actually working at the AND and OR gate level, and instead you're using higher level concepts in the FPGA. For example, they have built-in lookup tables and RAM units that they use to create your circuit out of. These are what you saw listed when you were shopping for different FPGAs and didn't know what they meant. You can also look into their user guides and see cool diagrams of these blocks and how they implement different features. Again, I'm just geeking out, but I love this stuff. It's good to roughly check over this and make sure nothing crazy is done, especially if you're using RAMs, because sometimes you'll define a RAM in a way that can't be done using the built-in hard RAMs, and your entire programmable circuit will be used creating your exotic RAM by mistake. Speaking of RAMs, that was my next experiment. I wanted to use the built-in RAM and initialize them with memory. Using the built-in RAMs and initializing them with memory is often painful, but it's super important to most FPGA designs. Back in rust-hdl though, creating a RAM was super easy. I just add it to my strut and set the size of what's stored in memory and how many address bits I want to have. When working with hardware, you're constantly having to swap between things like address bits and the actual size of RAM. For example, if I have 4 address bits, then that creates 2 to the 4 or 16 possible memory locations. Also, it's important to remember that the data we read from the RAM will have a 1-cycle delay. Now I just need to wire up my RAM ports and update. I set the read address to the switches on my FPGA, the clock to the clock, and I set all of the write values to false, which effectively makes this a ROM. I also set the output of the RAM straight to my LEDs. Finally, in default, I just need to set up the RAM. Here, for whatever reason, the memory is stored as a B tree, but I just insert a couple of test values and create the RAM. Now, when I flash the board, I can hit the switches and my RAM values displayed on the LEDs. Very cool. I can also look at the report from Vivado and see this actually used the hard block RAMs on the chip, which is what I want. Finally, for my big project, I decided to do a VGA implementation. It'd probably be smarter to do something practical like a UART connection so I can debug easier, but VGA is cool and I really like having visual results more than text and LEDs. This video is already getting absurdly long, so I'm going to blitz through the VGA design, but basically we get our timing numbers from a reference site, and we look at the diagrams to see what the monitor expects for the outputs. We need a V-sync signal to go once a frame for some period of time, and every row of pixels we need an H-sync signal to go low. We also have a pixel clock value which tells us how long each pixel should be on the screen. Clocks are again another massive discussion, but I really don't want to make this a true clock because those run on special networks on the FPGA, and reading data sources from different clocks requires a bit of care. Also, I don't really have a great way to get this exact clock without setting up a PLL, and I only know how to do that in Vivado, so I'm just hoping that the monitor will be forgiving and accept my 25 MHz clock, which is just 1/4 of my main clock speed. I set up my VGA driver strut, which has the output for the sync signals and if a pixel should be displayed and its coordinates on screen. I also keep a couple of internal flip-flop counters so I can count the time when I need to send the sync values. In Update, I wire up all my clocks and use one of rust-hdl's pulsers to create my pixel clock. It's kind of a bit janky to work with because it doesn't seem like it's meant to create a 1 clock pulse, but it works for me. Now whenever that ticks, I want to add to my X counter, and if my X counter is too high, I'll set it to 0 and add to my Y counter. I also set both back to 0 when the Y count is over its max value. Here, I make sure I'm setting all of the values in this block because I'm hoping that it'll get implemented as a multiplexer. Also, synthesis to a Verilog module seems to not work with constants, so forgive the magic numbers. I developed and simulated with const, but I had to swap them out for the final build. Next, I have the block checking if it's time to send the H-sync signal and the V-sync signals. And then finally, I returned out the calculated screen X and Y. I ran into some limitations here where the Verilog being generated was incorrect, and I had to write to internal wires to get the correct values. This is a super janky implementation, and the pixels will jitter, but I'm just playing around with the tools for now. Now on top, I can use the pixel values to set the different color outputs of the VGA when it's time to display an image. I had to do a lot of simulation and debugging to get this working, but it's super cool to see something actually appearing on the monitor. Next up was displaying an actual image. I grabbed a quick crate that let me get the pixels out of a PNG, and I set up my RAM with the pixel contents. Then I wired up the pixel coordinates to the read address and the data to the colors and just kinda hoped my image would work. But here we hit one of the fundamental problems with images. They are huge. A 640 by 480 image at 12 bits per pixel is 460,000 bytes. My poor FPGA doesn't have near that amount of RAM. So instead, I took a page out of the old Apple II computer and created a reduced resolution image. Basically, you can trade resolution for colors, or you can reduce the color space to get an image to fit in the RAM. Or you could just be an adult and use the off-chip RAM, but I'm too lazy for that. After some fiddling with the wiring, I got my PNG on the screen, which was again super fun. As my true final project, I wanted to create a text display. I wanted to have one memory basically be my sprite or font memory that holds how to print the text, and then I wanted to have a second memory to hold the ASCII values of every character on the screen. If you haven't seen stuff like this, I recommend Retro Mechanics Explained, which has beautiful videos explaining how tricks like this made the old NES and SNES games possible. I'm really pushing the video length now, but this is just implementing the same features we've already used. I create my font display block, which takes a screen in and gives out a single bit pixel. I also have my 2 RAMs internal to it. I wire up the basic addresses for the RAMs and make them read-only ROMs. Then I do some horrific bit casting and multiplications to get the address of the current character. Using multiplication like this is a bit expensive, but again I'm being lazy. We could talk for hours about the trade-offs here and the better ways to implement this. Then I do more bit casting to get the address I want from the font RAM. Here this is cool because my characters are 16 by 16, so the offsets into each sprite are actually just the bottom few bits of the address. This is a much cleaner FPGA solution, where everything is wired straight into the RAM with no crazy multiplication in addition. Finally, I get out my pixel value, and in top I duplicate all of the color channels to create my black and white image. After loading the wrong font file a few times, I eventually get my results to appear on the screen, and I've never been happier. Overall, it was deeply rewarding to get back into an old hobby, and I had a great time learning how to tie Rust into hardware development. The ability for the library to generate Verilog from a Rust design was super impressive, and I love all of the work they've done. In my free time, I'm probably going to contribute some code to this project, because I just really want more people to try out FPGA design and to have fun creating hardware. I did run into a couple of bugs, and even had to hand modify the Verilog myself, so I don't think this is production ready, or even beginner friendly yet, but I have high hopes for its future. This was again a super weird video, but I just wanted to take some time away from Bevy so I can be fresh going into the game jam this weekend. Let me know if you want to see more hardware stuff from me, because I really love this, and I would love doing a RISC-V implementation in Rust, and maybe even get the Rust code running on a CPU designed in Rust. As always, thank you to my wonderful Patreons, and I hope you can forgive an off-topic video every once in a while.